Hello everyone. So, yeah, in this electrical circuit laboratory, today we'll be learning about and verifying Thevenin theorem and maximum power transfer theorem. We should have already learned about Thevenin theorem in series. What Thevenin theorem says that if there is a bilateral circuit, it can be represented by a voltage source and a resistance in series of it. The voltage source is called Thevenin voltage and the resistance is called Thevenin's resistance. Now, there are certain limitations of Thevenin theorem. Firstly, the Thevenin theorem is not applicable if the circuit is non-linear. That is, if there is transistors and diodes involved, the Thevenin theorem will not work. Again, it will not work if there are unilateral elements like diode present in the circuit. That would enable the current to flow in one direction and not the opposite direction. In those cases, Thevenin theorem doesn't work. Theorem cannot be used in magnetically coupled circuit as well. So there are certain limitations. We are not focusing on the limitations at this moment. At this moment, we are focusing on the theorem itself and verifying the theorem. So here we have a circuit. So consider this portion over here, R1, R2, R3, this portion and Vs. These all things are black box. What is black box? Black box means, suppose your computer is a circuit. You don't know the components that is being used inside the computer. In the similar way, almost everything, your computer, TV, almost everything, you know it is composed of electrical and electronic components, but you don't know the components. So let us assume that this part of the circuit, this part, is a black box and we don't know the components. We only have two output nodes, A and P. Now what Thevenin theorem allows us to do is Thevenin theorem allows us to model this thing using one voltage and one resistance. So you have already learned it. I will still discuss various ways of doing it. The first way of determining Thevenin theorem is finding the open circuit voltage and short circuit current. So at first, let us build a circuit. We have a voltage source, DC voltage source, and 3 resistances. The load resistance has to be removed for measuring the open circuit voltage. So we have our PSpice here. We go to our parts. We create R. We have resistances. If we look at the circuit, resistances. Okay. I'm rotating the resistance by pressing Ctrl R. You can do the same if you want. So we have 3 resistances, and again we go here and VDC. We select VDC, which is our DC voltage source. Now we have to connect the wires. Let's connect the wire. I'm not telling you how to connect the wires because you have had already 4 or 5 labs, so you should know all these things. So I've connected wires. I need a ground, G and G. So you can choose ground analog or ground earth, any one of them would do. So I'm choosing ground analog. Now the thing is, see this, and you can consider this. From these 2 points, you get output. So there are different ways of measuring the output or seeing the output. At this point, I think our purpose will be served if we just see the voltage of this node, because since this node is grounded, the voltage of this node is 0. The voltage of this node will give the voltage across these 2 points. That is the open circuit voltage. In the actual circuit, there is supposed to be a load, but in order to measure the open circuit voltage, what we do is we remove the load at first. So there is no load at this moment. We have removed it. Let us see the parameters R1, R2, and R3. So from the experiment or from the lab chip itself, we have to choose Vs is equal to 10 volts, and R1 is 1 kilo ohm, R2 3.3 kilo ohm, and R3 4.7 kilo ohm. So this is 3.3k, this is 4.7k, and this is our 10 volts. So the circuit is done. So first thing what we need to do is we need to save the circuit. You can save it anywhere as you like. I would save it in my desktop. I'll create a new folder here. So I'm naming it Thev. So I've saved the circuit. Now we have to go to setup analysis and bias point detail. The bias point detail will show us the voltage and current of all the nodes. I don't think we need to switch on anything else. Close. Now if we simulate it, here we have simulate. Simulation is going on here 100%. So simulation is complete. Now here we have the voltage display and current display. If we could click this, we get the current display. We don't need the current at this moment. What we need is voltage. So at this point our voltage is 5.875. It is worth noting. So let's just note down in let's just note down in a notepad. So our Thevenin is equal to V open circuit is equal to 5.875 volts. Now one thing is to be noted. See, I have written Thevenin is equal to V open circuit. If you have studied this already in theory, then there should be no problem in understanding this concept. If you haven't, the Thevenin voltage is the voltage that you obtained across the output of the circuit when you disconnect the load. So here we have disconnected the load. The next step would be to measure I short circuit current. So in order to measure I short circuit current, what do we do? At first we don't need to see the voltage at this moment. So let's zoom out a bit. Now this is supposed to be the two nodes where we connect the outputs, and for measuring the open circuit voltage we have kept these things open. For measuring short circuit current, what we would do is we will shorten these two paths. So if we shorten these two paths and we simulate again, so see, through this node the current flowing is 0 ampere. Why is it 0 ampere? Because this is shorted by this path. So what is the current that is flowing through here? This entire current is flowing through here. So the short circuit current that we have is 3.03 milliampere. So let's note that down in the notepad as well. Excuse me for a bit. So here notepad, I have short circuit current is equal to 3.03 milliampere. 3.03 milliampere. Now we know Thevenin RTH, Thevenin resistance. We know resistance is equal to V by I. So V open circuit voltage divided by short circuit current. So if we take out the calculator, what would it be? Let's check. Our open circuit voltage is 5.875 and short circuit current is 3.03. So our Thevenin resistance is 1.9389. So 1.939. Since the current is milliampere, our voltage would be resistance would be kilo ohm. So Thevenin resistance is 1.939 kilo ohm. So this is one way of determining Thevenin resistance. There are several other ways of determining this as well. So the second way of determining Thevenin is by using the maximum power transfer theorem. So what does the maximum power transfer theorem say? The maximum power transfer theorem states that a resistive load will receive maximum power when its total resistive value is exactly equal to the Thevenin resistance of the network as seen by the load. That is, if we see here, if we connect a load here and the resistance of the load is, if we see in our notepad, the resistance of the load is 1.939k, which is the Thevenin resistance, then the maximum power will be delivered to the load. So what we do here, firstly we don't need to see the current anymore, and what we do here is we delete this. We click this and press delete. We press our resistance here, R. We press a resistance here and connect the resistance through. So this resistance is our load resistance, RL. Now what we could do is we could actually put the value of this resistance as 1.93 or whatever that we have found in other method, and we can use it here, but that wouldn't make any sense, because firstly we have already determined in another method. We are looking for a separate method, and secondly we can calculate this thing. We can find the open circuit voltage, short circuit current, and determine as well, but that wouldn't be really helpful. Why won't that be helpful? That won't be helpful because you see the problem again remains the same. The problem is, see this, if you put you don't know this circuit, this is a black box. You just know you have a black box, and for example if you see it here, we have this box, and outside this box we have two ports, A and B. You're connecting your load resistance to this port, so you do not know what's happening inside the box. So what's your how do you determine the Thevenin resistance? The first method we have seen, open circuit voltage, short circuit current. The second method is you put our load resistance, measure the voltage, and measure the power through the resistance. Then you put another load resistance, measure the power again. You keep on putting different load resistances and keep on measuring the power through it. If you continue to do that, you'll see that you'll find a graph of a power. The graph is supposed to look somewhat like, wait a second, the graph is supposed to look somewhat like this. So graph will reach the peak at a point. So in the x-axis you'll have the resistance, and in the y-axis you'll have power. So if the graph looks like this, so at the maximum power, if you find out the resistance, that would be your Thevenin resistance. So let's see how we can achieve that in our experiment. So since this RL will be changed, we need to sweep RL. So what we do, we use parameter, we use its value as x within third brackets. Then what we do is we insert as another part called param. We insert the part param, we double click on it and name one. Our name one is x. Save attribute. Value one is, at first we have to put a value. Let's put a value here. Whatever you put as a value here actually does not matter, because it will be swept anyhow. So we press OK. Then we go here, setup analysis. In the setup analysis, what we need to do is we need to DC sweep. We need to enable DC sweep and click DC sweep. So what we are sweeping, see, we are not sweeping voltage, we are not sweeping temperature, not current source, not model parameter. Here we have global parameters. So we are switching, since all the others are not true, this must be true. So we are switching, we are sweeping global parameters. What is the name of the parameter? Name of the parameter is capital X. What is the start value? Let's take start value as 0.1. Let's increase it by 0.1, and let the n value be, say, 10k. Starts from 0.1, ends at 0.1, and increment is by 10k. And the sweep type can be linear, octave, decade, anything, or you can list different values based on which it will be swept. So what does linear mean? Linear means that it will start from 0.1 and end at 10k, and it will increase with a step of 0.1, that is 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, like that. If you choose octave, what happens is you have a start value and you have an end value. If you start at 0.1 and if you put another value, say 10k, so you get start and end value. Every 10 times it will take this number of points, that is from 0.1 to 1. Suppose here you have given 10k, here you have given 10. So what would happen is from 0.1 to 1 it will take 10 points, from 1 to 10 it will take another 10 points and measure, from 10 to 100 it will take another 10 points, from 100 to 1000, from 1000 to 10,000. So with every multiple of 10 it will take 10 points each. You can increase the points. The more points you have, the smoother the curve would be. So here we have linear sweep. Start value is 0.1, end value is 10k, increment is 0.1. So we are choosing this, we are placing. Okay, so DC sweep is done. Now here we are sweeping this, and at the same time we are supposed to measure the current through the power through this resistance. So how do we measure the power? We can measure power by measuring the voltage and the current and multiplying them. So what we are doing is we are giving a voltage marker and a current marker, and will be multiplied. Actually these would not be required if we delete it. See, so what we need to remember is we'll be measuring power across RL. So what we do is we have completed set analysis and we press simulate. So it's simulating slowly. After simulation, what happens is the x-axis automatically becomes a variable that you have swept. So in this case the x-axis automatically becomes x, or the resistance. And now what do we need to do? We need to place the y-axis. Now what will the y-axis be? For the y-axis would be power through RL. Let us see if there is power. Okay, there is just voltage through RL and current through RL. So what we can do is, so voltage through RL, here we use multiply current through RL. So this would give us power through RL. So it can be done in several other way. Here you can find power, use power from here as well. So we are not using it here. So voltage through RL into current through RL. Okay. This graph is not required. Okay. So see, the voltage at first, the power at first increases and it gradually then decreases. So we have to find the maximum point or maximum power transfer theorem. Since the theorem is maximum power transfer theorem, we have to find the maximum point. So we click here, toggle cursor, and we find the cursor peak. So this is the peak. At this point we neither know we don't know the resistance that is associated with it. We can just see a point. We can approximate, but there is no need to approximate. You just put mark label here. So you see x-axis shows 1.9325, y-axis shows 4.4508 milli. So the power is the maximum power is 4.4508 milliwatt at 1.9325 K. This is the Thevenin resistance. Now let us compare it with our measurements. We see our other earlier measurements was 1.939 K and it shows 1.9325 K, which are almost similar. So you see, by this method you find R Thevenin. You can find R Thevenin as well. So what we are doing is, what we have done in this experiment is, in this experiment at first we determined V Thevenin by determining the open circuit voltage. Then we determine R Thevenin by dividing the open circuit voltage by short circuit current, and then we determined then we verified the maximum power transfer theorem, and we have seen that the maximum power is delivered to the load at the when the load resistance is equal to the Thevenin resistance. So for your report, what you need to do is you need to simulate everything. The first thing that you'll be needing to do is you need to solve the circuit by hand. That is, I'll be giving you the lab reports and you'll be having the circuit. So you'll solve this circuit by hand. By solving, you can use node analysis, mesh analysis, or whatever you want. So solving this circuit, you'll find the open circuit voltage and short circuit current. From those parameters you'll measure the Thevenin voltage, Thevenin voltage and Thevenin resistance, and you'll compare the Thevenin voltage and Thevenin resistances that you have found in the experiment. The next thing you do is you'd simulate this. Simulate this and get the required graph, and from the graph you'll also determine the maximum power and maximum the resistance and maximum power. So then what we do is you'll calculate you have already calculated the circuit by hand. So you'll put a resistance RL of 1.9375 K and you'll measure the power. That is, you'll manually find out the maximum power through the load resistance, and you'll compare this value with the value that you obtained obtained from the equation. So your task is, the circuit is given, you'll find the Thevenin voltage, Thevenin resistance, and maximum power through calculation by hand, and then you'll simulate and you'll just use screenshots and provide all the necessary graphs and results in your report. You already know what the format of report is. I would still write it in bucks so that you can answer this easily. Now another thing is to be noted that I don't know whether you have been told in earlier experiments, but I'll be telling this to you now. When you export a graph, see, it's black and you cannot read this very well. So you do not take screenshot of the graph. What you do is you click on the graph, you press right mouse and click properties. You increase the width of the graph so that it's more clearly visible. I think I've increased it too much. You can choose the third one from the top, it works fine. So after increasing the width of the graph, what we do is you press print. Okay, file, print. After print, you choose here Microsoft print to PDF. There will be different ways for different computers. You just have to select something that shows print to PDF. After that, you press OK, and it will tell you to go over. It will ask you where you want to print it. You choose your file and you name something. I'm naming it Thev and I'm saving it. So once you have done this, you'd go to your folder you have created. See, there is a PDF file called Thev. If you double click it, the graph would look like this. That is, graph will be very much visible now. So you should remember this. at no point you should take a screenshot of this graph, because this does not work well at all. So this is it for this lecture. In the next lecture we'll be learning about RC circuit and how to implement them using PSpice. Thank you.